We're going to learn the idea of trigonometric substitution method by trying this example. Integral of square root of x squared minus 1 over x to the fourth power dx. So first of all, I want to know that if you try just the basic substitution method, what we call U substitution, or integration by parts, those two methods will not help you to solve this integral. Try to apply those two methods as an exercise, see what happens, but the idea is that with those two methods, you're not gonna make things look easier or simpler for integration. So we need something different. Well, and that different will be trigonometric substitution method. This is how we think about it. So in this integral, I have the square root. And in general, square roots, especially when it's a square root of some kind of expression, some kind of polynomial, that makes things a little bit more complicated. So it would be nice to get rid of that square root, right? Now, how can we get rid of the square root? Well, one way is to square it, but to square, in order for us to square the square root, we have to have an equation. So it's like when we square one side of the equation and we square the other side of the equation, that works when we have equality. Well, here we don't have an equality, it's just one expression, right? So that's not going to work. Now, another common situation when square root can be cancelled is that when we have something square inside it, right? So it's like square root of something squared. Now, first of all, I want to make a note that in this case, we cannot just perform any algebraic operations like square root of x squared and then square root of 1. Remember, square root cannot be split up over the difference, only the product or quotient. So if I have plus or minus within the expression, I cannot split up the square root. So that's not going to work. No algebraic manipulations are going to work here. So that's where trigonometric substitution comes handy. So this is how we can think about it. If you remember, most basic trigonometric identities come with squares of functions. So for instance, like the most basic ones are, so we have, of course, if you remember, sine squared of x plus cosine squared of x equals 1, right? You probably remember that one. And from that one basic identity, we can obtain some other identities. Well, among them, let's say 1 minus sine squared of theta equals cosine squared of theta, right? Hopefully you recognize that one. Also, we have from there, we can also obtain identities that connect tangents and secant, and then cotangent and cosecant. So the one that connects tangent and secant can be written in this form: 1 plus tangent squared of theta equals secant squared of theta, right? So our goal will be, so hopefully you recognize those. Our goal will be to look at the expression inside the square root and resemble one of those basic identities. And it's always going to be only one that we can think of. So what's the structure of that expression? The structure of that expression is we have something squared, well, x squared minus 1, minus a number. So what kind of identity resembles that? So in other words, I have to think some kind of trig function squared minus 1. Now, if I look at the list that I have here, I don't have that. I have 1 minus function squared, but it's different than function squared minus 1, right? Remember, when we have a sum, we can switch terms with no harm, right? But if we have a difference, we want to follow the order. So 1 minus sine squared of theta is not same as something squared minus 1. But I haven't actually wrote one more identity that we can obtain from here. So if I look at that second one and I subtract 1 from both sides, right, then I'll have secant squared of theta minus 1. So I haven't wrote that one yet. So hopefully you can follow minus 1, and I'm also swapping sides. So secant squared of theta minus 1 equals, and then it's going to be tangent squared that's left on the other side, tangent squared of theta. Okay, so that's the one. Now, as soon as I wrote it, now I can see that the left-hand side of this identity resembles the expression that's inside the square root. Why do we want to make this connection? Well, because if I can create the left-hand side of that identity inside the square root, then I can always replace it with the right-hand side. But the right-hand side is just tangent squared, right? So if I write it as secant squared of theta minus 1, then I can replace it with tangent squared of theta. But then what is square root of tangent squared? Well, it's just tangent, right? That's where I can cancel the square root. That square root will be canceled with the second power. And that's what I am aiming towards. So if that's what I want to do, then that's how I'm going to think about it. I want my tangent to turn into secant theta, right? Well, why is it secant theta? Because if x is secant, then x squared is secant squared, right? So that's the idea. I'm going to write this down. I want x to be secant theta, because with that, I'm creating the left-hand side of one of the identities. Now, let's write down how the numerator is going to look like. I'm going to move it over here. So that means that my numerator is square root of secant, now squared of theta, minus 1. And that's what I will replace with tangent squared of theta, and I will get rid of the square root. But every time we do substitution, any kind of substitution, we want to remember that our new integral should only have the new variable. By the way, what's the new variable now? The new variable is theta, right? We used to have x here, but now we have theta. So that's the new variable of integration. So it means that everything has to be rewritten in terms of theta. So I shouldn't see any x's in here. Let's go back to the original integral. So x to the fourth power has to be written as in terms of theta, and then dx has to be written in terms of theta. But how do we perform that? Well, with the denominator, it's easy, because if x is secant of theta, it means that the denominator will be, so x is secant of theta, so the denominator becomes secant to the fourth power of theta, right? How about dx? Well, to see what differential dx equals to, I just have to find it here, right? So if x is secant of theta, then what is dx? Then dx is derivative of secant, which is secant theta tangent theta. Just refresh that. Look at the table of basic derivatives, right? You'll find that derivative of secant is secant theta tangent theta, and then d theta, right? So what it means is that dx, differential dx, has to be replaced by this expression. So that's what I'm placing instead of dx. And as I continue the integral over here, I'm going to write this down. So instead of dx, I'm writing secant theta tangent theta d theta. Okay, so now everything is in terms of theta, and hopefully you already can sense that how a lot of things will simplify here, right? It's going to be a trigonometric simplification, so let's see what we're going to obtain. Well, I can already see that, for instance, that secant theta can be divided out with one of the secants from the denominator, so power becomes 3, right? But going back to the numerator, I can see that inside the square root, I will have tangent squared of theta, so secant squared of theta minus 1, I got replaced with tangent squared of theta, over, now secant is to the third power, times that secant is gone, so it's just tangent theta d theta. Of course, now this is where it's all happening. That square root is going to be canceling the second power, so I only have tangent left. I'm not skipping any steps for now since it's the first example, but you probably can see how, we could have simplified it a little bit quicker. Okay, so square root and square got cancelled. It's just tangent squared, just tangent in the numerator, secant cubed, and then that tangent d theta. Okay, well, let's simplify. So we'll multiply tangents, and then we'll perform more of trigonometric simplification. So tangent squared of theta over secant cube of theta, d theta. Okay, so don't attempt to integrate this until you simplified your expression as much as you could. And if you remember, the way to simplify this, we can just rewrite tangent and secant in terms of sines and cosines. That's one of the tricks from trigonometry, right? In the numerator, if I rewrite tangent in terms of sine and cosine, it's going to be sine squared of theta over cosine squared of theta. And now the denominator, secant. Secant itself is 1 over cosine, right? But since it's cubed, it's going to be 1 over cosine cubed of theta, d theta. Now we obtain this complex fraction. To simplify the complex fraction, we need to change from, we need to switch to division, right? So where I have fraction bar, main fraction bar, I will write division, or think about it as division, which I will switch to multiplication. So numerator, sine squared of theta over cosine squared of theta times, so that division I'm switching to multiplication by the reciprocal of the denominator. So reciprocal of 1 over cosine cubed is cosine cubed over 1 d theta. So here we can divide out cosine squared. That's gone. That means that our integral is sine squared of theta cosine theta d theta. Okay. Next will be to think how to integrate that, but let's recap real quick all the steps that we've done so far. So our first step was to perform the correct substitution, right? To notice what kind of formula, I should say, or identity, trigonometric identity that expression resembled, and based on that, perform the appropriate substitution, right? Once we replaced, that was step 1. Once we replaced everything in terms of new variable theta and all those trigonometric functions, the next step was to simplify the resulting expression as much as we could. Now, once you simplify the expression, then you're going to end up with an integral that you have to evaluate, but cases will be different. In some cases, you're going to just end up with basic trig function, like integral of cosine, right, which you do right away. Sometimes, like in this example, you'll have to, be creative, or you have to think about the appropriate method of integrating this. And let me remind you that to evaluate this trigonometric integral, we have to perform substitution. Now, that substitution has nothing to do with the original substitution that we did at the beginning. It's just, again, the matter of evaluating this integral and doing whatever it takes to evaluate it. So to evaluate this integral, we're going to perform the following substitution. We're going to let u be equal sine of theta. Well, that means that is u, right? So I will have u squared. But then du, differential u, is the derivative of sine, which is cosine of theta d theta. And based on this, I can see that cosine theta d theta, this portion, has to be replaced with du. That's just the method for, it's just the substitution method that we use for trigonometric integrals, right? And that means that I will have integral of u squared du, and that I can likely integrate pretty quickly, right? So it's going to be u to the third power over 3 plus c. Now, after this u substitution, we have to go back to the original variable of integration, which in this point was theta, right? So u I will be replacing with sine theta. So that's going to be a sine cubed of theta over 3 plus c. But is that my final answer? Well, no, because what was the original variable of integration, like from very beginning? That was x, right? So it means that we need to return to variable x. Let's go, and that's the last step. So step 3, integrate whatever it takes to integrate this trigonometric integral, whether it's basic, it's quick, or not basic, so then you have to do something like that. And then step 4, return to the original variable of integration, which is x. How do we do that? Well, our new variable theta has to be replaced with x. Let's go back. Remember, we always find the way of returning to the original variable as we look at how we introduce the substitution. So here we have, here it says that x is secant of theta. But what is theta? By what do I need to replace theta? Well, one way you can say, well, theta is the inverse secant function of x. But that's not going to be too helpful because now my answer will look a little bit, well, it's look like it has to be simplified anyway, right? If I put sine cubed of secant inverse of x, it's just going to be something that requires simplification anyway. So this is how we would usually do it to find what to replace theta with. Based on this substitution, we're going to do the following. So secant, I'm going to rewrite it one more time. Secant equals x, right? Which is same as x over 1. Agree? I'm going to construct a right triangle, so that's where we'll have to refresh basic definitions or triangle definitions of trig functions. Here's the right angle. Now, one of the angles I should name theta. Here it is, either one of them. So if I can find what sine of theta equals to, then that's going to be the base case scenario, right? Because if I know what sine theta equals to in terms of x, then, well, I'll just put that expression here for sine of theta. But how do we find sine of theta? Well, if we know that secant of theta is x over 1, we'll have to refresh definition of secant. So secant is reciprocal of cosine, but what is cosine? Cosine is the adjacent side to hypotenuse, right? That means that secant is reciprocal of that, so it's hypotenuse over adjacent, which means that x represents hypotenuse and 1 represents adjacent side. I'll label that on my triangle. So hypotenuse in this triangle is here, that's x, and adjacent side is over here. Adjacent side to angle theta. Okay, but what is sine of theta? Sine of theta, based on its definition, remember it's opposite side to hypotenuse. So from this triangle, well, I will be able to find sine. It's just I'm missing the opposite side. How do we find the opposite side? To find the opposite side, we're going to use the Pythagorean theorem. So if you remember, according to the Pythagorean theorem, it's lag squared plus lag squared equals hypotenuse squared. Right? Since it's our first example, we're going to write this aloud, but in the future we can do it a little bit quicker. So one lag is unknown, right? That's the one that we're trying to find, that's the opposite side. So I'll just say lag squared, that's unknown, plus another lag squared is 1 squared, which is 1. And the hypotenuse here is x squared. So from here, that unknown lag squared is x squared minus 1, right? I subtracted 1 from each side. And then what is the lag itself? Lag is square root of, I'm just square rooting both sides. It's square root of x squared minus 1, right? So this missing lag, it's actually square root of x squared minus 1. And it's also the opposite side of angle theta. So now we can find its sign or express its sign this way. Opposite, by the way, that's O. Opposite side, which is square root of x squared minus 1 over the hypotenuse. Hypotenuse is x over x. So knowing what secant of theta is in terms of x, we were able through this process to find sine of theta. And that's the idea that we'll use for all other examples as well. So now we know that sine of theta has to be replaced with this expression. I am going back to the answer. Okay. So that's what sine of theta equals to, and that's where I need to place that. Now, sine is cubed, so it means that that expression will be cubed. Let's write this all down. Now, 3 in the denominator I'm going to write as 1/3, as the coefficient 1/3, so it's out of the way. Sine, I'm replacing by square root of x squared minus 1 over x. And then since sine is cubed, that expression is going to be cubed. O plus c. And to finish this, I'll just maybe, simplify it slightly. What I'll do, I'll say it's 1 over 3 times. What I can do, I can square both the numerator and the denominator. So the denominator, it's a little bit easier. It's going to be x cubed, right? Now the numerator, I can think this way. That's same as x squared minus 1 to the power 1/2, right? That's square root. But then power 1/2 being raised to the power 3, that's where I'll have to multiply them, right? Multiply the powers. So that means that the numerator, I can write like that, x squared minus 1 raised to the power 3/2. 3/2. And that's how I will leave this answer. Plus the constant. Okay, so that's step 4. One more time. First step is to think about the appropriate substitution so that expression inside square root ends up resembling one of the identities, right? Once you perform substitution, then you would need to simplify trigonometric expression as much as you can. Once you simplify, think how to evaluate the resulting integral. And once you evaluate that integral, then don't forget to return to the original variable of integration. And that's going to be the process of thinking how the original substitution can be used to express some other functions of theta in terms of the original variable of integration. So that would be the way.